Hey all, in this video we're going to look at solving quadratic equations, and specifically we'll look at 4 different methods: factoring, the square root property, completing the square, and quadratic formula. Dependent on what we're asked to solve, often one of these methods is the better one relative to all the others, so I'll try to explain when to use which method as I go through the examples. Starting with factoring, if you are not great at factoring, if you have to take a lot of math after this class, you should get great at factoring because it's going to keep coming up over and over and over. But if you have an equation that factors, that is by far the easiest way to solve it relative to like plugging into the quadratic formula or something. And again, these factoring skills are going to show up all over the place, so very much worth the effort to get good at factoring. For this first example, it's just a GCF. We have x squared plus 3x, so each of those terms has an x in it. So I can factor the x out front, and that's going to leave behind an x plus 3 equals 0. And so remember, when we're solving using factoring, we have this equals 0 on this side, and what this means is I have something times something equals 0, which means either the first thing has to be 0 or the second thing would have to equal 0, because 0 times a number would be 0, likewise a number times 0 would be 0. So whenever we have a GCF, even if this had been 7x, what that means is x equals 0 is one of the solutions, which makes sense because every term had an x, so if I put in 0 for x, 0 plus 0 does make 0. And then when we have a factor like this, what we're doing is we're setting that factor to 0 and then solving for what would make that true. And so we bring the 3 over and we get x equals negative 3. Usually we don't show that step, but we just realize that if we have x plus 3 as a factor, negative 3 is what would make that come out to 0, so we're going to have a 0 at the opposite side of the factors. This next one, so still in factoring, doesn't currently equal 0, so that's kind of our first step for factoring problems. If it isn't already set up to 0, and actually solving any of these, if it isn't set to 0, that's our first step, is to get it in standard form. So we'll do that right here by subtracting the 63 on both sides. And that gets us an equation in standard form. And now I can ask myself, are there two numbers that multiply to be negative 63 that I can make add to be 2? And there are. And if you can find those numbers, that means it factors. If those numbers don't exist, that means you're going to use one of the later methods, either completing the square or the quadratic formula. But if it factors, you can just go straight to the answer right here. So 9 times 7 is 63. And those numbers are 2 apart, and since that 2 is positive, then the big number, the 9, needs the positive, and the 7 needs the negative, so that they add to be positive 2 and multiply to be 63. And then remember, our zeros, or solutions, have the opposite sign of the factor, so this would be x equals negative 9, and that's because if I put negative 9 in there, negative 9 plus 9 would make 0 times who cares, would still equal 0, and on this side we'd have x equals 7. So those are our solutions there. This next one is this does have a common factor. There's a common x in both of those. So get that pulled out of there first. And then what's left in the parentheses is our difference of squares. It's an a squared minus b squared. So remember that those factor to a plus b and a minus b, or x plus 5, x minus 5 in this case. We started off with x cubed, which means we're going to likely have 3 solutions. There's cases where one of them is repeated, so it counts twice. But in this case, we have our 3 x's there, so we're going to have x equals 0 as our first solution, negative 5 as our second solution, and 5 for our third solution. For this one, but it really helps if you remember that this is an a squared plus 2ab plus b squared from the factoring review. And then you remember that that factors to a plus b quantity squared, because if I wrote out a plus b, and I FOILed all that out, what I would get is something of this form. What tips me off that's one of these is it has perfect squares on both ends. So that means it's a good shot that it's one of these factoring formula ones. Assuming that a squared is matching up to the 49x squared, then that means that plane A would be 7x, because 7x times 7x gets us back to 49x squared. Likewise, if b squared is matching up to that 4, and then since it's a plus, but if b squared matches to the 4, then plane b would be 2 quantity squared. At that point, we should check and make sure that this middle term actually works with the assumption that we're making that it is one of these perfect trinomial squares. So remember, to do that, we can do the 2 in the formula times a times b. So 2 times 7 would be 14, times 2 is the 28 that it should be. So that is factored correctly. And generally, if you see the squares on the ends, it's almost always one of these, but it doesn't have to be one of these. It can be. You can have squares on the ends with a different middle term. So it is good to check. With this one, 7x plus 2, that's a little harder. With these, it's pretty easy to just look at them and know negative 5 and 5. This one's going to be negative 2/7. If you can see that, great. But if not, here is how you get that. We're literally just setting this factor to 0 and solving to see what x would have to be to make it come out to 0. So I'll fire that 2 on over and then divide both sides by 7. So if it helps to write that out, by all means do so. But that's the same as what we're doing over here. Just over here, it's easy enough to, we can usually look at it and see. This last one, so it is not in standard form, so I'm going to distribute that x through and bring the 28 over. So x times x would make x squared, x times 3 would make 3x, and then instead of equals 28, I'm going to subtract 28 on both sides, have minus 28 equals 0. So again, that first step of getting it in standard form so that I can see what I have. From here, and even if we had these later techniques, my first thing I would try is there two numbers that multiply to be 28 that add to be 3? And if I can find those, great, I'm done. That's what makes factoring really nice. If those don't exist, again, then we would go on to one of these later methods that we're going to see here in a second. 7 and 4 multiply to be 28, and I can see that they're 3 apart. Once I write them down, the middle of this is positive, so again, that would be one where the 7 has to have the positive and the 4 has to have the negative, so that they add to positive 3. If it had been a negative 3, then my signs would be backwards. The 7 would have to carry the negative, and the 4 would have to carry the positive. So we got our factors, and then we just write down our zeros, so negative 7 and x equals 4. Next up is solving quadratics using roots. So this only works when you have something squared that you can undo with a root. So if you look at all 3 of these problems, x squared, chunk of math squared, likewise another chunk of math squared. So when we see something in that form, we can use the square root property to solve. If we think of one that's a little bit easier, x squared equals 4. When I square root both sides of that, remember that we need the plus minus, so that x equals plus or minus 2, which makes sense because if I say 2 times 2, that would make 4. If I say negative 2 times negative 2, that also makes positive 4. So anytime we're using the square root property, we have to use a plus minus. So here I'll square, and I'm using a square root to undo that square. So plus or minus there. So square root of x squared makes x. That's our reason for doing that. And then that's going to be plus or minus square root of 147. 147 we need to check and see if we can simplify this at all. And if you try dividing that by 3, you'll see it goes in 49 times. So I'm going to think of that as 49 times 3. And then when I simplify, we're going to have plus or minus. Square root of 49 would bring out a 7 and leave behind the 3. And notice this is not 7 plus or minus root 3. This is all just these 7 root 3 and 147. Those are the same number. We're just writing them in a different form, so we're not adding or subtracting in there. We're just simplifying out that 49. For this one, let me write it out. So it's the same principle. Since I have this whole chunk of stuff in the parentheses squared, I can't, like if it was 2 squared plus x squared, that you can't do the root and take the individual pieces, but as long as the whole thing is a square, which this is, that allows me to use the square root property. So for instance, for what I was just saying there, a squared plus b squared, that can't be simplified. I can't apply the root across addition, but as if I have a plus b squared, not very good, but hopefully you can see what I mean. That way, when I take the square root, I'm undoing that square on the outside. So here, this is going to be 2x minus 1 equals plus or minus square root 9 is plus or minus 3. So this is two separate answers, either plus 3 or minus 3. I will keep solving here and show you what to do with that. So I'll add 1 to both sides of this. So that means we're going to have 1 over here, and then that's going to be plus or minus 3. And then we'll divide by 2. And I get this expression. So this is two separate numbers. This is x equals 1 plus 3 over 2, or x equals 1 minus 3 over 2. So 4 over 2 would be 2, and this would be negative 2 over 2, and that would equal negative 1. So that's how that plus or minus works, is you actually have two completely separate answers to solve. Sometimes we write them together. I'll show that on this next one. But when the square root comes out to something nice, and like the perfect square here of 9, and we just get a plain 3, at that point we can keep simplifying until we get to numbers, so we have to keep going. This one you'll see I'm going to have a root in the answer, so this I'll leave just in terms of plus or minus. So h minus 8 quantity squared makes 20, and we'll do our root on both sides. Boom, boom. So the square root of all of that squared would just be that h minus 8, and then plus or minus root 20. So square root 20 is 4 times 5. So I'm going to bring out that 4 as a 2, and I'll leave behind a root 5. And then I would need to add the 8 over to this side, so h equals 8 plus or minus 2 square root 5. And this is two distinct answers. It's 8 plus 2 root 5 and 8 minus 2 root 5. If the answer box asks you to write your answers as a list, it's looking for this version. Sometimes they just have boxes where you can type in the 8 and the 2 root 5, depending on who programmed the question. But both of these are acceptable in terms of pencil and paper answers. So this next version we're going to look at solving quadratics is by completing the square. And people mostly don't like this one, which is it's a little hard to remember. And if you're good at it, it's actually a really easy way to solve them. It's easier than quadratic formula. But that said, people generally don't prefer this one for solving, and it works for a bit more limited number of problems. It works for all problems, but it gets cumbersome to do on certain types. All of that said, we'll use completing the square a little bit in a later section. And in the next class, there will definitely be completing the square. So even if you don't love it as a method for solving quadratics, it's worth getting just a little practice with it because it will show up in the next class for sure. Our steps for completing the square are going to be, given a quadratic, we bring the constant term over to the right. If this a doesn't equal 1, we divide through by a. And what I would say with regards to that is if a doesn't equal 1, just use the quadratic formula, and this will be the easier way to solve it. So I never really use that second step. The middle one is sort of the magical one. We take half of the middle term, we square that, and we add it to both sides. And what we're doing there is we're completing the square. That's where the name comes from. We're making this into a perfect trinomial square that we can factor to one of these forms, and then we can use the square root property like we just looked at to finish solving it. All of that makes it sound really complicated. I will do just one example with it, and it is actually it's a pretty easy way. It's easier to complete the square than it would be to use the quadratic formula to do this, but again, it's a little bit harder to learn out of the gate. And once you're good at it, it's actually a bit easier. When I would personally use completing the square is when this leading coefficient is 1 and that middle term is even. And the reason is we're going to have to take half of the middle term. So if the middle term is odd, now it's a fraction, and then you square the fraction, and then you have to add that fraction to both sides, and now you're working with a bunch of fractions, and that's not easier, so that's where I would use the quadratic formula. But for this example we have here where this is 1 and this is even, this is exactly where completing the squares is actually easier. And again, we'll use it as a technique to get things into a form. We'll see it this quarter, but next quarter it shows up in several sections, so it is worth knowing. So for this one, let's go ahead and do this. So t squared plus t, 10t. I'm going to leave myself some space there because I'm going to end up adding something. And then our first step was to write that 19 over to this side, so that becomes minus 19. A is 1, so we don't have to worry about the second step. The third step is the kind of magic one where we take half of 10, that is 5, and then we square it, which makes 25. Oops, that didn't work. And that's the number we're going to add to both sides of this equation. So the reason we're doing that is because we're trying to take t squared plus 10t and force it into being an a squared plus 2ab plus b squared. We're trying to find this value that completes the square. So we took half of the middle term to get rid of the 2. The a is like the t, so now we're just left with b when we take half the middle term. That 5 is the b, and then we would square it, and that tells me what I have to put on the end. The reason we do that is so that we can then write this as t plus 5, quantity squared equals 6. And then it's really easy to solve from there. Then we just do the square root on both sides. And t plus 5 is equal to plus or minus root 6, and then subtract the 5 over. So t equals negative 5 plus or minus root 6. And that's it. So if I do this in the quadratic formula, this particular one would have a lot of reducing, and it would actually be harder math. So for me, I prefer if a is 1 and b is even. I think completing the square is easier. If not, though, you can use the quadratic formula for any quadratic. It will work on all of them. It's just not always the easiest tool. And that is where we are to now, is the quadratic formula. This flipped over. I'll say one more thing back here real quick, just because I was checking my notes for how I wrote out the answer. This one might be the answer box where it says write it as a list, in which case these two solutions could be written negative 5 plus root 6, comma, negative 5 minus root 6. So those would be your two distinct solutions without using that plus or minus notation. Okay, so solving using the quadratic formula. So remember, the quadratic formula is x equals negative b plus or minus b squared minus 4ac all over 2a, where that's a, that's b, and that's c. You can solve any quadratic using the quadratic formula. You just write it in standard form, and a, b, and c, plug them in here, grind out the math, and it will be solved. If the problem factored, which this one is actually going to be one that would have factored, it was probably easier to just factor it. That said, quadratic formula will work. So let me show you what this will look like with one that factors, and then with some that don't factor, and getting the decimal answers for these, and just sort of how to simplify them towards the end. Okay, so we got x equals negative b, so that's negative 14 plus or minus square root of 14 squared minus 4 times a is 3, and c is negative 5. And it's all over 2 times 3. So we'll go down here, negative 14 plus or minus, this would be 196 and then plus 60. So this is 196, and there's minus and minus there, so I just count up the minus signs. If I have one negative, it's minus, 2 negatives, it's going to be plus, 3 negatives, it's going to be minus again. So 196 plus 60 under the root over 6, and that would be x equals negative 14 plus or minus square root of 256 over 6. And then this, if you throw that in a calculator, I'll come up here with it, it's going to come out to negative 14 plus or minus the square root of 256 turns out to be 16, and that's over 6. So this is one of those ones where we don't have a root left here, so that means we have to actually keep combining until we get to two solid numbers. So we'll have x equals negative 14 plus 16 over 6, or x equals negative 14 minus 16 over 6. So here that would be 2 over 6, or reduce our fraction, we get 1/3. Here that's going to be negative 30 over 6, and negative 30 divided by 6 would make for a negative 5 as our second solution. So when these come out to non-root type numbers, rational numbers, what that means is this would have factored in the first place. Depending on how good you are at factoring, it may have been harder for you to factor that than it was to just run it through the quadratic. But that's what that means when those are rational, is that it did actually factor. This next one is supposed to solve by the quadratic formula, give both the exact answers and the answers ran in 2 decimal places. So that's a pretty good sign that that one doesn't factor, since we're going to get answers to 2 decimal places. So let's see, this time it's going to be r equals negative 3 plus or minus 3 squared minus 4 times a times c all over 2 times 4. So that's going to be negative 3 plus or minus, that will be 9, and then 8 times 4, 32, so 9 plus 32, that would be 41. Let me just rewrite that. Over 8. And again with that double negative, so it's 9 plus the 32 to get that 41. So those are the two exact answers. So they would be, if I wrote them kind of side by side, negative 3 plus root 41 over 8. And then, oops, it's r though, my bad. I'll just do that. R equals negative 3 minus root 41 over 8. And then we would need to put these into the calculator. So you type in negative 3 plus square root 41, and either you need to put parentheses around that, or just type that and hit enter, and then hit divided by 8, enter. And when I did that, I got this one to be 0.43 rounded to 2 decimal places. And same thing over here, minus 3 minus square root 41, enter, divided by 8, enter. And for that I got negative 1.18. And then this last one, this last one is just showing with complex numbers. So it's the exact same thing, but this time we're going to get imaginary solutions. So 3 and 11. So we have x equals negative 3 plus or minus 3 squared minus 4 times a times c all over 2a, so 2 times 4. So x equals negative 3. Whoops, I just totally messed up. I missed that 9 there. Apologies. I was like, why is that not looking like my notes? Sorry about that. Let me try that one more time. It is not set to 0. I think I did the same thing when I wrote the notes. I missed that. So I need to subtract that 9 over. So 4x squared plus 3x, and that's going to make a plus 2 when I subtract the 9 over. Okay, so then we got x equals negative 3 plus or minus 3 squared minus 4 times a is 4, and now c is 2, all over 2a, so 2 times 4. So negative 3, 9 minus 32, so that would be negative 23 under the radical. Over 8. And then that negative, like we saw in the earlier section with complex numbers, we would write that as I root 23 and over 8. And so again, if we had to write that as the two distinct solutions, if it said give your answer as a list for the answer box, negative 3 plus I root 23 over 8, comma, negative 3 minus I root 23 over 8 would be the two solutions.